So another episode of the Money Button documentation series. We're covering Money Button itself, but not just Money Button, also the technical things that you need to know about Bitcoin to be able to develop apps on Bitcoin SV. So today we're going to talk about Mnemonics, aka BIP 39. So there's a standard way to basically write down a string of words that you use to generate a master private key, which you use in a wallet. There's more than one way to do this, but the most common way is called BIP 39. So let me just dive into my presentation. What I'm going to do is I'm going to share my screen, and then guys just let me know if something goes wrong, because it's hard for me to tell when I'm in this full screen mode if something is broken here. Okay, are you guys seeing the presentation correctly?
Yes, you're seeing the presentation on full screen.
Okay, great. Okay, so first of all, let me go back here and okay, so first of all, we already saw this, that we have hierarchical deterministic keys and hierarchical deterministic wallets, and we'll link to this presentation. The basic idea is that we want one master key that we can use to derive a bunch of different addresses for a wallet, primarily so that there's only one key that you have to back up, while at the same time allowing you to have many different addresses, and at the same time allowing other people to generate new addresses for you if you want them to. And the only con we really talked about so far was basically that there's one sort of security gotcha with the standard way to do this, which is that you can't simply share private keys the way that you might be able to with a bag of keys approach. Not that you would normally share your private keys anyway, but there are some protocols where it actually does make sense to share private keys, and you can't simply do that with hierarchical deterministic wallets. But that's actually a really minor issue, and you can do it if you're doing it correctly, and you probably don't want to share private keys anyway, so it's not like you're going to be doing that under normal circumstances. Now, there's actually one more con that I think we brought up, which is simply that, okay, so we've reduced everything to this idea of having a single master extended private key. But there's still one con, which is, I mean, no one's going to write this thing down. This is a really long, I mean, this is an example of a BIP 30, or sorry, a BIP 32 master extended private key. It's just clearly way too long. Yes, it has base 58 check encoding and all that stuff, so that if you make any errors, you can detect them. Nonetheless, I mean, no one's going to bother to write something crazy like that down. So it would be nice if there were a way to have a key that you can easily write down, because then what you could do is you could back it up on paper, put it in a safe somewhere. You could, you know, depending on your level of paranoia, put it inside of a bank deposit box or bury it underground or who knows what. But it would be nice if it were convenient to write down rather than writing down random gibberish like that. And so the solution to this is, or one of the solutions anyway, is what's called BIP 39 Mnemonics. And basically the idea is that we generate a list of words, and the list of words also has a checksum that we use to derive a master extended private key. So this string of words is much easier to write down than writing down one of those crazy base 58 check encoded master extended private keys. So an overview of what this is and how this works is sort of as follows. So we'll kind of cover this in a bit of detail, but this is just the overview first. So the idea is that you start with some random entropy. So you just generate, like you normally would, a bunch of random entropy, usually like 128 bits to 256 bits. We compute a checksum of this. We concatenate the checksum to the entropy. And then using a standard list of words in a particular language, so English or Spanish or Japanese or so on, whatever your language is, use a standard word list. And it has to be a certain number. It has to be 2048, because we're going to convert 11 bits per word, or 11 bits at a time, into a word chosen from the list of 2048. You can optionally then add a passphrase to the list of words, so that basically if you want to write this down and you're worried that somebody will be able to steal the piece of paper that you write this down on, you can add a passphrase to it that you memorize, so that even in a worst case scenario where someone steals it, they actually don't know the passphrase. And so you can just keep that memorized or put it in a different place or something like that. Then you hash the words. So this is like an irreversible hashing algorithm, so that no one can go backwards. We'll talk about that, probably why people did that in a minute. But now that you've hashed it with SHA-512, you have 512 bits, which is long enough to have both a private key, and a chain code for a BIP32 master extended private key. So that's just an overview. Now let me kind of go through what all that is in detail. So first of all, we start with random entropy. So in this case, I'm giving an example where we use 128 bits because 128 bits is adequate. You can go all the way up to 256 bits according to the BIP39 standard. However, if you use more bits, then the number of words is larger. And so depending on what your use case is, well, seeing as 128 bits is still well into the impossible to crack territory, it's actually adequate for most uses. So we use 128 bits because that means that the number of words that people have to write down is actually smaller. So anyway, the examples use 128 bit, but if you want to use a large number of words, you can keep that in mind and you can do it that way. So we start with 128 bits, random string there for entropy. Then what we do is we compute the SHA-256 hash of the entropy, find the first few bytes of that, and it looks like I think it's 4 bytes. I can tell looking at the example, this is a real example here. So we take the 4 bytes of the checksum. Sorry, it's 1, 2, 3, 4. 4 bytes of the checksum, add it to the end of the entropy, and now we have a sort of a checksum on the value. So if something were to go wrong, you have a checksum of it. Now what we do is we convert an entropy, let's just call it a buffer, which is the entropy plus the checksum, into a list of words. So 11 bits at a time, and you have to do some binary arithmetic to parse out 11 bits, at a time from this. You take 11 bits, and starting from your list of words, and again, this is a real example here. So the words speak, pig, round, topple are indeed the first 11 bits, the second 11 bits, third 11 bits, fourth 11 bits, and so on of the string here, and construct your mnemonic. So then you end up with something that looks like this, which is your mnemonic. So it comes directly from the entropy, including the checksum. So if you were to write down one of the words wrongly, you could do error correction, and you could do things like, well, the word is wrong, but this other word actually is correct. And so you would be able to detect and correct for errors. So for instance, if you had a piece of paper that got wet or something like that, you actually might be able to recover it even if the information is slightly damaged. And you would also be able to tell whether you had written it down wrongly. Now what you do is you can append a passphrase or have this sort of jokey, my super secret passphrase here. And you can add, it's roughly speaking, you add this to the list of words. And as far as the user is concerned, there is just also a password. This is optional. We do not do this in MoneyButton. The user has a different password in MoneyButton. We don't make use of the BIP39 password, but for people that want to do that, you can. And this is just a way to allow you to write down your mnemonic on a piece of paper, basically. And if you ever get robbed, somebody steals it or it's compromised for some reason, they would also have to have your password to be able to reconstruct the keys. So then what we do is now with the mnemonic, we use something called PBKDF2, which is, we've covered this before, SHA-256 HMAC. So that is SHA-256 inside HMAC, which basically means we have a key and a value. And what we do is we take the mnemonic and we have the mnemonic without the passphrase and the mnemonic with the passphrase. We pass that into SHA-256 HMAC. Now what PBKDF2 is, it's a standard way of hashing things many times. Because in the history of hash functions, one of the uses for hash functions is that very often you have a web service where you want to log into a web service or a service of any kind. And early on, like in the 90s, people would get their databases hacked all the time and leak out everybody's passwords. So they learned that if you just hash the password, rather than store the plain text password on the server, you can protect against database leakages. And so originally people used really weak, what at the time were thought strong and later discovered to be weak hash functions like MD5. Then they basically got smarter and realized as people were able to leak databases, that your server gets hacked, leak a database with and crack MD5 or something like that, they could steal your passwords anyway. So they started getting sophisticated in making these deliberately slow hash functions. And one of those is PBKDF2. And all PBKDF2 is, it's just a standard way of applying the same hash function over and over and over again. So in this case, BIP39 requires PBKDF2 with SHA-256 HMAC 2048 times. So it just runs the same hash function 2048 times. And I don't actually know why they did this, because this wasn't explained in the spec for BIP39, but I suspect they probably did it that way because they want to make it, basically if the hash function were broken, they don't want people to be able to invert it to get your mnemonic, I assume. I'm not really sure though, but in any case, that is there in the spec, and you have to use PBKDF2 to derive the hash value. Now we get something that looks like this. So this is 512 bits. That is long enough that we can split it up into a private key and a chain code, and then we can import that into BIP32, and now we have a BIP32 master extended private key. So that's basically it. So that's how we go from a mnemonic into a master extended private key. Now there's one other thing I want to talk about, which is actually a different BIP, because this kind of completes the idea of how to make a Bitcoin wallet. Once we have the master extended private key, we've already talked about how we have hierarchical deterministic addresses, but there's still an open question over what paths do you use to derive the addresses. And there's a standard path structure called BIP44 that is used by most wallets. And basically the way this one works is, the idea is that you have an account for each cryptocurrency that you hold. And you can have more than one account with the same wallet. So I'll just describe what we're looking at here in these paths. You can see, for instance, the first address of the 0th account is im/44prime/0prime/0prime/0/0. What that means is im/Bitcoin, Bitcoin is 44 prime, slash 0 prime means something like the standard way to do it or something of the sort. Then there's another 0 prime, which means the 0th account. Then there's a normal 0 that just means external facing addresses. And then the final 0 means the first address. And so you can see how to derive for the same account. You keep the second to last 0 the same. That means it's the same account. And you can derive the second address and so on. If you want to generate a different account, you use account number 1. So that's shown in the second 2 examples there. And again, this is a real working example. So that's an actual address that came from these keys. And so basically what is often the case for different cryptocurrencies is, instead of using 44 prime, they use something different. So for, I don't know, we at Money Button, we use 44 prime just because our software basically goes back to the original Bitcoin, and we're still using the original Bitcoin. So that's just what we use as 44 prime, because that was written in the spec originally. But for Litecoin or something like that, I mean, people use different numbers there in a lot of cases. The first 0 prime is just a way of allowing you to use your Bitcoin key for some other thing besides accounts, but that's not normally used. So if you're sort of doing it in the standard way, you're probably only using the very first count and the addresses that come out of that. And what we do at Money Button is, okay, so you then have this idea of the distinction between the external and the change addresses. So the external ones are the ones that you're supposed to share. The change addresses are the ones that you use inside the wallet. Money Button does not use the change addresses. We only use the external facing addresses, which is sort of the second to last digit there. We do that just out of sheer technical simplicity, because we aren't using the extended public keys to allow, other people can't access your extended public key. So there's no privacy problem with this approach, and this makes our software simpler. But this also does mean that you can't synchronize your key with a different wallet. All you can do is export out of Money Button. If you try to use a different wallet that does use the change addresses outside of Money Button, that will not be seen by Money Button. So that gives you an idea how that works. So then there's this other idea of BIP44 wallet recovery. So if you were to export your mnemonic from Money Button into Electrum SV, you can rescan all of the addresses basically and find the money again. So there's a standard algorithm for recovering all of the money in a mnemonic. And so what this means in practice is, so basically how it works is, for each account, you try to scan out 20 addresses. And if any of them were used, then you keep going until no more of them are used. And the number that matters here is 20. You scan out by 20. And what that means is it's a really bad idea to generate more than 20 unused addresses in a row. Because if you were to import that key into a different wallet software, it might not find all of the money. So your money is still there, but it might not see it. And so it would be really irritating to deal with. So this is kind of a limitation of the way all these BIPs fit together, is that you can't just derive an arbitrary number of unused addresses. So it's a minor limitation. And what that means in practice at MoneyButton is that we have to occasionally reuse the same address because someone sends a payment late or something like that. Every once in a while, there will be an address that gets reused because we can never derive more than 20 of them in a row, or we risk not being able to recover the money in a standardized way. So in conclusion, we have the standard for BIP39 that's used by most wallets, and it's used by MoneyButton. That is a way of having a easy to write down list of words that are your wallet and can be used to derive all of your addresses in a deterministic way. And you only need to back up this list of words once, and you can always recover your money later on. And the standard way to do all of the wallet recovery and what paths to use to ensure that other wallets that can do recovery can recover the money is to use the BIP44 path structure and the wallet recovery stuff. So that's it for the presentation. So before I go on to code or anything, you guys have comments or questions about it, any of that stuff?
Just a little comment on my side. Basically, when you create the words for the mnemonic and you use the 11-bit stuff to, basically that is a number, and you have a list of, like the list of words is standard. So it's supposed that every wallet uses the same list of words. That's something nice. And the other thing is that those words, I don't know, when I read that, it was like just a curiosity, were selected in a special way where they're trying to be as different as it can be, and they're supposed to not be two words that sounds really similar or that are written down very similar, because that might cause confusion. Yes. So it's like there is a selection for every language of yes. words that works in this for this use case, basically. Yeah. So that's something nice about the standard.
Yeah. So for the word lists that have been standardized, and there may be 5 or so word lists that include English, Spanish, Japanese, Chinese, Italian, French, if I remember correctly. There might be more now that I don't know about, but those are the ones that are included in our library. The words.
They're all in GitHub also, so if you want to find it, you just they're really easy to find.
Yes. Yes, we can. Well, in fact, we'll of course we'll link to that as well, so that so people can see that stuff. Yes, you can look at the list of words, and they're smartly chosen so that there's no confusion over, I don't know, 2 words that look similar but are different by a single character or something like that. So they're all pretty smartly chosen.
I was going to ask about special user case, because I saw that some wallets ask for just one word to recover mnemonic. So instead of asking you or the user to complete your entire mnemonic phrase, they just check with just one word of the entire 12 word.
Well, if it's one word that is not possible, and they must be using some other mnemonic structure or something like that, because you could do some totally different standard. If they're using BIP39, what they let you do is you can type in the first character of a word. Is that what you mean, or like actually a word? Because if you type in the first, like the letter A, you can then see a list of all words that start with the letter A, and well, you know,
right, kind of an autocomplete and choose the one that you're. But I was asking because I think I saw, I don't remember, it's just one word. Maybe there's 3 of them, but they don't ask you to complete your entire phrase.
I believe I know what you're mentioning. Like usually when the wallet gives you your mnemonic by the first time, there is some kind of little puzzle to solve. And it's another thing that is nice, because you might write it down and have some kind of little mistake.
And correctly,
so to write it again in some way, there is some way of quick puzzle to see if you actually write it down correctly.
Yeah, verification.
For example, Yes, in Money Button, what we do is we show you the words in a wrong order, and you have to order them. And if they're in the right order, that's enough. There are other wallets that they made using something shorter, like what is the 7th or the 6th word? And if you answer correctly, they consider that you write it right. That's what you say,
they establish the order of the phrase, and they ask you just by one, but you need to know in which order that word is set in order to recover your money. Okay.
But no, it's to for the wallet to make sure that you write it down correctly. But to actually recover your money, you need the complete password.
The 12.
The complete mnemonic.
Okay. Yes. Thank you.
And just another comment on the usability here, because mnemonics are an improvement over what came before. But I hope that no one is under the illusion that this is the end of usability improvements. I mean, ideally, the user won't even have to write down the mnemonic. So there are a number of different ways we can solve this, and we might talk about some of these ideas later on. But just for instance, you know, having so the threshold signature scheme that, you know, InChain is working on for for Bitcoin SV is one way to deal with this. You can have it where the user doesn't know their own keys, but because they have another way to authenticate with a number of other services or people or something like that, you can allow other people to sign on your behalf and recover your money if you were to lose access. That's just an example. Other things you can do are embed keys inside hardware, so that maybe your device has the keys inside of it. That's already starting to happen. There's some of the modern smartphones have actually keys built in, not for Bitcoin, but for other uses of cryptography. And you can either use it for Bitcoin, or they can add, you know, sort of special features just for Bitcoin. So hopefully this is not the end of the usability improvements. And although it's better than what came before, we'll keep doing everything we can to make this stuff more user-friendly, so that hopefully the user doesn't even have to write down a mnemonic ever, while still being able to recover their money if they lose their password or something like that. Okay, so let me just dive into the code and show some quick examples really quickly, so for people that want to see how this actually works in the software. So let me open up my terminal here, and all right, screen share one more time. Okay, so as usual, I'm in my terminal, and what I'm going to do is, so one of the differences with the mnemonic library, because it actually has a bunch of words, you don't necessarily want to load these 5 different or 6 different giant word lists into your application. So you have to load BSV/mnemonic. It's put in a different place so that it is not included by default.
You put like 2 names, 2
var.
Yes.
Var mnemonic is what I meant to say, and then var BSV, because I want to make sure I have access to that as well. Okay, thank you. So anyway, so I had to load it differently. But now that I have this, I can do things like, so to make a new mnemonic, I'll just say mnemonic.fromRandom, assuming I actually exposed this one unlike I did last time. Mnemonic.fromRandom. Okay. So then I can just say all that just happened is it literally just generated a new one for me randomly, and then I can just output it. And this is what you would...
The first one was called Mnemonic. It's a type one, the original one.
I actually typed it in wrong. I typed it in when I created the variable. Okay. I'm going to throw away that wallet and make a new one. I haven't sent any money.
It's another typo. It's like a really hard word.
Oh, gosh. Mnemonic equals, it's a hard word. Yes, it is it's an irritating word to have to type in.
There is still a missing N between.
Okay. It is not having a good day with my keyboard today.
Yes.
Mnemonic. There you go.
Mnemonic. Cool.
Okay. So I just generated a new one, and under the hood, what this said was generate the entropy and do the checksum and all that automatically. And that's almost it. So now the only other thing that matters is, I mean, the user would actually write this down, and you can then do things like import a mnemonic. And as I think about as I type it in, make sure I don't type it in wrong. Mnemonic.fromString, mnemonic.toString, and still mess it up. Mnemonic.fromString. This one might not be there, but what I'll do is, here, what that really is a different error. I can never remember whether the toString and fromString methods are there or whether I have to do it like this. Okay, so I just created it using the constructor because in this case I can pass it in. So now I should get the same one back again, which I do, of course. Now what I'm going to do is, so the most important thing is given a mnemonic, so I imagine the user types it in or something because they're recovering their wallet, I can now generate a master extended private key for the user. So this is, like, for instance, the way Money Button works is this is all done client side. So given the user's mnemonic, they then can do HD private key dot from seed mnemonic dot to seed. And what this is, so basically given my mnemonic, I can output the seed. This is the part that runs that hash function. So it takes the mnemonic and runs PBKDF2 2048 times on it and gets me two seed, and gets me this thing here, which can be used directly inside the from seed method on an HD private key to generate the private key. Now, there's also a convenience method because they have some nice convenience methods built in here. So I can do something like mnemonic dot to, I think it's like that HD private key. Yeah, something directly like that. So this is another way to, to directly generate the master extended private key for this. And it should be that these are the same and they look like the same. So there's a nice convenient way to do that there. So then you can go off and do all the other things like given my extended private key, and I won't spend too much time on this because we basically already talked about this, but I can then immediately derive 44 prime slash 0 prime slash 0 prime slash 0 slash 0 would be the first address. And this will, it's actually the first key, but using that key, I can then do things like dot private key. It doesn't know that, but I know that I can do this here. I think I can do two address. Is that, yes, it does. So I got two address of two string. So I'm generating the first address of the first account in the wallet. And so that's it. I mean, now you can go off and make a wallet because you can generate all the addresses and basically ping a blockchain node to ask it whether the address has ever sent or received money, and you can reconstruct an entire wallet that way. So that's it. Let's see.
A quick question. I imagine that you can create, like this example, create a 128 bits mnemonic, right? That you could create different sizes. I imagine that there is some kind of parameter.
So unfortunately, they don't make that easy. There's no, we could change it or something and add that in if somebody wants it. You can't just type in a parameter 256 instead of 128. The way that you do that is you actually have to generate your own entropy. So I'll do something like this, BSV dot crypto.
We are not seeing your screen, the terminal. I don't know if.
Yeah, oh, good point. Let me make sure I share my terminal here so you see my terminal as I type this in. So I'm just typing in, I'm generating the entropy. So new entropy is dot from random. Oh gosh. Crypto dot random dot from, or sorry, get random buffer 32. There we go. So I just generated my own new random string. So this is slightly error prone, but that's just what you have to do. And now that I have my own entropy buffer, what I can do is I can make a new mnemonic. Let's call this one mnemonic 3 equals mnemonic dot, or say, I think the way it works is I type in like new mnemonic and entropy. And so I pass in my own entropy there. And then I can do stuff like this. And now it has a larger number of words. So they don't make it easy, but but you can do it. The other thing, just so that people can see something like this, I'll do one different thing here, which is I'll generate it in Spanish because it's pretty easy to show how to generate different languages as well. So basically, so one of the ways to do that is here. I think I can just type in mnemonic.words.Spanish, I believe. I think it's.
It is Spanish uppercase, yes.
Yeah. And then mnemonic 3.2 string. is Spanish. So,
Right.
and that's a long one because I'm still using the same entropy as before. Now it's actually, since I did it that way, note that although this is the same entropy, the word list is completely different, obviously, because it's a different language. And because that is hashed to create your extended private key, it's a different wallet. So just because it's the same entropy does not mean it's the same wallet. If it's a different word list, it is a different wallet.
Right.
Okay. All right, let me just show one more thing for completeness here. So we also have the documentation, and I'll just briefly glance through that. Right here. So we have some basic information here, which is pretty much what we just said, and shows you all the methods and everything that you can use to derive everything. And including information about what paths to use if you're building a standard BIP44 wallet and all that stuff. Oh, you know what? I think I said something wrong earlier. Now that I think back about this, I think that the 44 may actually be, I'll have to review the spec, but these are the standard paths. And I'm trying to think, maybe the 44 was actually about, because it is BIP44. So I feel like they might be saying that the reason why it's a 44 there is actually, that is BIP number. But somewhere in here, oh, now that I think I stated it wrongly now that I remember this. This actually just means BIP44. The first 0 there actually means Bitcoin. So I think what I said was something like there was an unknown number or something because I couldn't remember. But that's just because the part that I forgot was actually the first one just means BIP44. This one means Bitcoin. This one means account number 0. This one means external address. And this one means the first external address. So that's what the numbers actually mean. They don't matter most of the time because if you're doing it in a normal way, you just use the same path over and over again and you don't have to think about it.
Great.
Okay. So to conclude all this stuff, so if you want to learn more about all this stuff, we're putting all this information on docs.moneybutton.com. So that's where all these resources are going. We're creating information, not just about MoneyButton, but about sort of Bitcoin in general so that people can really understand everything that they need to do to be able to build an application and hopefully even a business on Bitcoin SV. And we have our main website at moneybutton.com where you can find links to everything else. And because people are interested in this sort of thing, if you need help from us, you can come ask us questions in our Telegram group at t.me/moneybuttonhelp. And last but not least, we're compiling this information to a series of blog posts that are going to go on our blog, which is at blog.moneybutton.com. Right. I think, did I forget anything? I think that's everything.
No,
I think it's everything. Yeah.
Okay. All right. Then the next video will probably be on ECDSA. So we'll keep going until we've finished everything.
Awesome.
All right.
Great.